In class today, we started talking a little bit about examples of phase diagrams, and we didn't have very much time. We had about 10 minutes, so I thought I would make a little video and just go through some of these phase diagrams again and discuss them with you. So this is a phase diagram I showed for SiO2, silica, and we talk about silica as a chemical compound, but phases are crystal structures that are particular to that compound. So even though they may be chemically the same, they're different phases and they have different material properties, different heat capacities, different thermal conductivities, different diffraction patterns. So this is pressure versus temperature, and we've got this whole series, or this whole family of phases. We've got a little bit of liquid here, but you remember when we were talking about water, right? We had a liquid and a solid and vapor phase, and here we really have the vapor phase and liquid sitting over in this region, right? And this is a phase diagram showing pressure versus temperature, and then here is the vapor phase for SiO2. So it goes alpha quartz, beta quartz, beta tritonite, beta cristobalite, liquid, and this was 1 atmosphere. So at 1 atmosphere that goes through these transformations, and you get the same here: alpha, beta quartz, beta tritonite, beta cristobalite, and then liquid. So the vapor is sitting off this edge. And this was a single composition. If we had another composition, then we'd have another axis coming out, and that other axis could be some other constituent. For example, I showed this in class. This was 2 constituents. This is SiO2 and Al2O3. So in this binary phase diagram, we start out with what is this? This is cristobalite here. So this cristobalite is a line compound. Here we have molite, and here, which is a mixture of SiO2 and Al2O3, and then here we have alumina, and this is just another line compound. The molite is a solid solution, so it has finite thickness. Or the molite, I should say, can have a range of compositions. And then here we have a 2-phase region of molite and cristobalite, another 2-phase region, and then here we have cristobalite and liquid, molite and liquid, and here is a paratectic reaction. I wanted to go through an example of reading a phase diagram, and I think that I went through one in class, and I want to go through another example here. So this is an isomorphic binary compound. It's copper and nickel. So being isomorphic means that these two have the same crystal structure, and they have very similar size, or I should say sufficiently similar size, that they form a continuous solid solution from 100% copper to 100% nickel. So let's pick somewhere here. Let's pick here, actually. I'm going to pick, so you notice on this phase diagram, the bottom axis is giving you weight percent, and the top axis is giving you atomic percent. It's critically important that you pay attention to those units because they don't necessarily line up, and reading the wrong one will be a big problem. So let's pick 50 atomic percent to work with. So I'm just going to draw a dashed line to kind of guide the eyes. Okay, so let's say we're starting out in the liquid region, somewhere here, and at that point we have 100% liquid, and the composition is a 50 atomic percent nickel. If we then cool down, right, just before we cross the liquidus, we're still 100% liquid, and we have that composition of 50 atomic percent nickel. We cross into the two-phase region. We can now look at the composition by drawing a tie line. Let's draw that like that. So our tie line is perpendicular to our cooling path. And then we look at where the tie line crosses the boundaries, and now we draw a line from that intersection to the axis. This. So our composition of the total system is 50%. The place where this line crosses is about, let's call that 58%. And the place this line crosses, we'll call that around 45%. So reading this, there's, for an equilibrium structure, that there's two things we can get. We can get the fraction of each of the phases. So that's telling us, let me draw a picture here. That's telling us that if we have alpha, alpha, alpha liquid, if we could then separate out, just liquid and just alpha, 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 what fraction of the total system is made of liquid, what fraction of the total system is made of alpha, and we can specify that in atomic percent or in weight percent. We're going to do in atomic for this example. And the phase fraction of alpha is given by the lever rule, where basically you look at your tie line and you look which tie line crosses into the alpha phase, because this is a two-phase region, so it's going to cross into a single-phase region, the alpha, and that's here. And then you take the opposite line. So in this case, it's a different color to make this stand out. That orange line, and we divide it by total line length, which is this magenta line. So that means that the phase fraction of alpha is that orange line, so that's going to be 50 minus that line, which is 45, divided by the total length, which is 58 minus 45. And then we can get the phase fraction liquid. And one thing you could say is, well, we know it's all liquid and alpha, which means that if we know the alpha, then we know the liquid because it's just 1 minus F alpha. Or we could calculate it out, and to calculate it, we would then take the length of the green line here divided by the magenta line, the total width. And we can zoom in here again. And the reason we're taking the green line is because we see where the boundary, or where the tie line crosses into the liquid single phase region, and we take the opposite region, or the opposite part of the tie line. So that means that the phase fraction of liquid is going to be 58 minus 50 divided by 58 minus 45. So the total length. And that gives us the fraction of alpha and the fraction of liquid. That's one thing we can get. Another thing we can get is we can get the composition of each of these liquid and alpha, which we've separated out. And that comes from reading where the lines that we drop from the tie line intersect the axis. So we draw the tie line where the tie line crosses into the alpha region. That gives us the composition of the alpha. So comp of alpha, and we just go up and read that, and it's 58% nickel. 58 atomic percent Ni. And here's the composition of the liquid. So we read over here, draw the line over, draw it up, and that is 45 atomic percent nickel for the liquid and for the alpha. And that's basically how we read phase diagrams, at least working with them in equilibrium. If you go to talk about more advanced topics, such as phase evolution and non-equilibrium structures, then you have to start looking at more sophisticated techniques. But for this class, we're just going to be looking at the equilibrium structures, and you'll get the non-equilibrium structures when you take kinetics. Something I want to point out about this phase diagram is that it doesn't go to 0, right? This temperature stops at 1000. And that's because whenever phase diagrams start getting down close to 0 degrees Kelvin, odd things start happening. This is the phase diagram for copper nickel. So it's this phase diagram. But now it's going down to 200 degrees C. And you notice that all of a sudden you have other things happening. And this is these low temperature phase changes. These are due to what's happening, well, basically it's due to the third law of thermodynamics. And we're not going to talk about that here, but it's something that when you're taking your thermodynamics course or a kinetics course, you should be aware that at low temperatures we can get odd behavior. So that was looking at an isomorphic binary compound. Now let's look at the next most complex structure, and this being a binary phase diagram which has a eutectic. So this is lead tin, and one of the questions in the homework sets is asking what is the solubility limit of something in something else. So what we can do here is we can say, what is the solubility of tin in lead at 150 degrees C? So that'd be 150. Well, that, if we start out as pure lead, we form an alpha phase, and that alpha phase is the lead crystal structure and has the lead lattice parameters and everything that makes it pure lead. And as we start to introduce tin will start to substitute for lead on some of its atomic sites, and that lets us kind of go over here. So now we have some tin in our lead, and it's sitting on the sites, and we can keep going and keep adding tin until we reach this phase boundary. And that phase boundary is going to tell us that, okay, as soon as we cross over, well now we no longer have our alpha phase, we now have alpha plus beta. And this beta phase, if you look at that, this beta phase is a tin-rich phase. So what happens is we get precipitation of a tin-rich phase out of our originally lead-rich phase. So this line gives us the solubility limit of a tin in lead. And you can see that it changes with temperature. So at lower temperatures, the solubility limit is much lower. At higher temperatures, it is greater. And this certainly goes with our intuition. If you think about trying to suspend something such as sugar in water, right? You have higher temperatures, and it's easier to to create a solid solution. So let's take and read one of these phase diagrams. Let's imagine that we have some composition. Let's say, and again, we got atomic percent on the top, AT%, and here's weight percent. So let's say we have, and notice here they really don't line up at all, right? So 50% weight percent gives you what it looks like. So this is 50 weight percent. 50 weight percent tin gives you around 63 atomic percent tin, and then that's because there's such a large difference in the atomic weights here between lead and tin. But let's pick a composition. For example, here, 45 atomic percent. Well, actually, let's pick a weight percent, right? Let's do something different. We'll pick a 40% weight. So 40 weight percent tin. Okay, and let's say we take 40 grams of tin and 60 grams of lead, and we measure them out, and then we heat them up until they're molten, and that will put us, say, up here. And at this point, we have a homogeneous single phase. It's all liquid, and it has a composition of 40 weight% tin and 60 weight% lead. As we start to cool down, we cool down until we're, say, here. And now we're in this alpha plus liquid two-phase region. So in order to determine the behavior of our system, we can take and draw a tie line. So we can say, okay, what is the composition of the alpha? Well, where the tie line crosses into the alpha region, that's going to give us the composition of the alpha. So that says the composition of the alpha. What's that? That's around 10, it's around 17 weight%. So I'm going to write this over here. Comp alpha 17 weight%. And then the composition of our liquid. Do the same. And that is around, what, 40, maybe 46 weight%. So that means the composition of our liquid is 46 weight% tin. So that's weight% tin, weight% tin. Okay, now we can say, okay, we now know that at this point we have alpha, 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 and liquid, and we know the composition of these, of the alpha and the liquid. So if we could separate them out, alpha, 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 and liquid, we would know the composition of each of these subsystems, and we want to address how much excuse me, we want to address the question how much alpha in that total system, how much liquid in the total system, and we get that from the lever rule. So let's define this lever here. It's A. That one as B. So to determine the phase fraction of alpha, we see that, well, the tie line crosses alpha there, which means that we're going to use the inverse tie line, which is B. So that's the length of B divided by the length A plus B. And in this case, we have these. So we know that B is equal to 46 minus 40 divided by the total length, which is 46 minus 17. And then the phase fraction of the liquid is 1 minus the phase fraction of the alpha. Or if we want to write it out from the lever rule, that's going to be, well, the tie line crosses liquid here, so that means we use the inverse. So that's going to be the A region. A divided by the total length, which is A plus B. A plus B. And using what we have here, we can say that F liquid is going to be A So that's going to be 40 minus 17 divided by A plus B, which is 46 minus 17. Okay. Now, if we wanted to, we can keep cooling. And when we cross now in from the alpha plus liquid into the alpha plus beta, we now have a new structure. And let's say we're actually right up just below the eutectic transformation. Well, that structure looks like this. You know what? That structure looks like this. Alpha phase, and then some eutectic lamella. So we're going to have alpha plus beta phase. Beta and alpha. So we can ask ourselves, what is the phase fraction of alpha and beta? And because we're in the two-phase region, we can get this from drawing a tie line again. All right, there it is. So the let me zoom out. And now let's draw our vertical lines. So that is around 97%. And this vertical line is around, look at that, it actually almost lines up with this one. So it's again around 17. So the fraction of alpha is going to be, that's where it crosses alpha, so we take the inverse distance, let's call this distance B, this distance A, so it's going to be B divided by A plus B is equal to 97 minus 40 divided by 97 minus 17. And then the phase fraction of beta is A divided by A plus B, which is equal to 40 minus 17 divided by 97 minus 17. So we've got the phase fraction, and now another piece of paper. We can also get the composition. So I'm just right here. Composition of alpha is where our tie line touches the alpha phase. So that's going to be 17 weight percent tin, and the composition of the beta is 97 weight percent tin. So that beta really is very tin rich. Now another question we could ask is about the relative amount of microconstituent, right? So we could say what fraction is this eutectic type lamellar microstructure as compared to the primary alpha microstructure. And we can get that by going up and recognizing that when we transform from alpha plus liquid into alpha plus beta, what happens is right above the eutectic temperature, we have alpha plus liquid, and when we cool down, that liquid transforms. So this microstructure, originally just above that, looks like this. I'll try to draw it the same shape. Okay, well, I've done better drawing in my life than that, but alpha, 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 liquid. So if we can go back and determine the phase fraction of liquid, that'll tell us the amount of microconstituent made up of the lamellar microstructure. And we can do that again by drawing tie lines. So right above the eutectic temperature, we'll draw a tie line. And then we draw vertical lines down. So one vertical line will go here. So that looks like around 18%. And another tie line will go here. And that looks around 61%. So I've got 18 and 61, and we have the original, which is 40 still. So we can say the phase fraction of alpha in the alpha plus beta region just above the eutectic is going to be, so it touches alpha there, so it's going to be 61 minus 40 divided by 61 minus 18, right? It's going to be that distance over the total distance. And the fraction of liquid is going to be over here, so it's going to be 40 minus 18 divided by total length, which is 61 minus 18. And then when we cool from just above to just below, this liquid is going to become eutectic alpha plus beta microconstituent. And again, the method for doing this is the same as for the isomorphic composition, and it's the same for more complex phase diagrams, which I'm going to show you some examples of those now. So this is a phase diagram that is made up of magnesium oxide, MgO, and alumina, Al2O3. So our constituents are these two compounds, and we also have a intermediate phase, and that intermediate phase is, well, the composition here, which is MgAl2O4, which means that we basically have one MgO unit plus one Al2O3. But that, constitutes in weight percent around 73. But here at the top, this is mole percent or atomic percent, and if you look that gives us about 50. Well, not about, it gives us exactly 50, right? Because it's exactly a 1-to-1 ratio of the two. So again, it's critically important to recognize which unit you're reading in, whether it's weight percent or molar percent. Your textbook seems to do everything in weight percent. Other texts do everything in a molar percent or atomic percent. So let's look at this diagram. What I think is important is to recognize that anytime that you have the intermediate phase, you're essentially kind of almost, not always exactly this way, but many times it's almost as though you are being able to subdivide your phase diagram. So for example, in this one, look at this. If we draw a line here, right? Now we have two eutectic microstructures, right? Or two eutectic phase diagrams. Right, here's one where we have a MgAlO4 and MgO, and here is solid solution, liquid. That's going to be whatever, alpha plus liquid, beta plus liquid, and we have got a binary eutectic. And then on the other side, we have another binary eutectic. Right? We've got this large solid solution. Here is a line compound, and then we have Al2O3 plus liquid, and here we have MgAlO4 plus liquid, and then here's liquid. So that's a little eutectic line. So if you look at a lot of these compounds, even some of the more complicated phase diagrams, you get behavior which can be expressed as though you have a microstructure which is two subdiagrams. It's not exactly two subdiagrams, but it does look like it, and if you think about it in this fashion, it really helps clarify what's happening. So let's look at this and then talk about where it's going to deviate, and in particular, it's going to deviate from the binary eutectic we saw before if we're looking in this region in here. So let's say we have some composition, let's say, whatever, let's just pick, what's that, 60 to 70 weight percent. Sure, let's pick 70 weight percent. So if we pick 78%, we start up here in the liquid region, and then we cool down. This point here, we cross into this two-phase region, which is a liquid phase plus a MgAl2O4 solid solution. And because it's so kind of cramped in here, I'm not gonna, let me see if I can zoom in. You can see that we could draw tie lines here if we wanted to. Let me find pen. So we can draw tie lines, for example, that goes across like that, and then we could drop down and like that. So that is, let me zoom out, 70. That is like 66. And that is, say, 72. So if we ask ourselves, what's the fraction of MgAlO4? Well, that would come from 72 minus 70 divided by 72 minus 66. Whoop. Sorry. That's the fraction of liquid. So that's going to be, because the liquid size on this side, so we have to take this the small side, the small part of the lever arm for the liquid, and then the fraction of AlMgO4, that would be 70 minus 66 divided by 72 minus 66. And then the composition of the liquid is here, 66 weight percent Al2O3 and comp alpha, or not alpha, of AlMgO4 is 72 weight percent Al2O3. So we can keep moving. Let's say we keep cooling down. Until we're in the single phase region, and that single phase region is a single phase. So if we ask ourselves, what's the fraction of MgAl2O4? Well, it's 1, or 100%, right? Because there's only one phase. And we could ask ourselves, what's the composition of Al2MgO4? And the composition is 70 weight percent Al2O3. And the reason is because, again, there's just a single compound, and in equilibrium, all of the grains are going to have the homogeneous composition given by the phase diagram. And then we can cool down further. until we're now in this region. And what happens is you had Al2MgO4, and now you have some small precipitates of MgO that are coming out. And we can ask ourselves, what is the phase fraction and what is the composition? And again, we get that by drawing a tie line. Like this. And then determining the phase fraction by the inverse lever rule. So basically, that is huge, right? So the fraction of MgAl2O4 is, 98 parts would be the Al2MgO4, and then 2%, which is that little tiny bit, would be the MgO. So that this picture is actually pretty realistic. And then the composition of the MgAl2O4 we can get by dropping a line, and it's going to be like, again, around whatever, 72.5. So that's going to be the composition. 72.5 weight percent Al2O3 comprises this phase, and then the MgO is a line compound, so it's pretty much pure. So that's one phase diagram where we've seen a little increased complexity. I'm going to go a little faster here. This is another phase diagram. So this is magnesium and copper. And magnesium and copper have a fairly large difference in atomic radius, and as a result you get two different compositions. Here we get a line compound, so this magnesium is a line compound, so it is fairly, copper is fairly insoluble in this. Here's another line compound. It is Mg2Cu, and this is atomic percent. So at about 33%, well, at exactly 33%, because it's a 2-to-1 ratio, you get this line compound. And then if you go over here to 66%, we get another line, well, this one's not a line compound, this is a solid solution, but this is MgCu2, and this one has some thickness to it. You can see this is a solid solution region. And then over here we have copper, and copper seems to have, at around 400, has a solubility of around maybe 6% magnesium that can sit on the copper sites. But again, I drew these vertical lines kind of in my notes, and you can see that's a eutectic, binary eutectic. That's another binary eutectic, and that's another binary eutectic. So this is another example of a phase diagram that can be broken up into little sub-diagrams. And, you know, without belaboring the point, I'll point out again that if we had something such as, say, 50%, and we're up here in liquid, we cool down, and we wanted to talk about what the system was like. Well, we draw tie lines. And then we could read where the tie lines cross the axis, and then use the lever rule to give us the phase fraction and read the intersection to give us the percent. I mean, weight percent's up here, so if we wanted to, we could even draw these up and we could talk in terms of weight percent. Okay. Like that. So here is an example of a phase diagram with paratectics. This is aluminum nickel. So let's look at the regions and identify single phases and two-phase regions. So here is a single phase, right? It's a line compound. It sits in here. Here's another single phase, although this is a solid solution. This is a single phase solid solution. That's AlNI. Single phase, single phase, single phase. So we got single phase identified, which means that now between those we have two-phase regions. Give me two-phase. Here, here, here. So let's talk about what phases are present. Let's see if I can list this out. Al3Ni plus liquid. This is Al3Ni2 plus liquid. This is AlNI plus liquid. So do you see where that comes from? And this is Al plus liquid. So where that comes from is identifying the two-phase region between single phases. So here is pure aluminum. Here is pure Al3Ni. So this is a two-phase region of Al plus, let me zoom in, Al plus Al3Ni in this region. And then we have this line compound, basically a line compound of Al, and then here is liquid. So we have to have a two-phase region between these two single-phase regions. So that makes this Al plus L. Here we have the line compound, and it stops right here. And here's liquid, which means we have to have a Al3Ni plus liquid phase in here. Here's a two-phase region, which is made up of Al3Ni plus Al3Ni2. That's a two-phase region. This region comes up and it stops, which means that here we've got a single phase and here we've got a single phase, which means we now have a two-phase region between them, which is Al3Ni2 plus liquid. And then here is a single-phase region, it's a solid solution, and liquid, so we have a two-phase region between them. And you can go and basically map out your entire phase diagram that way. And when we talk about phase transformations, we talk about what's present. We'll start say here, and if we start in liquid, we come down, let me zoom in again, we come in, we cross that liquidus, and now we have Al3Ni2 plus liquid. We keep coming down, we cross, and when we cross, we've changed regions. We still have liquid, but now in this region we have Al3Ni instead of Al3Ni2. So there's a change, and these type of changes where we have a change in the solid. This is from having a paratectic. And then we keep cooling down, and here the Al3Ni is still present, but now that liquid has transformed into Al. So we can look at these phase diagrams and know what they are. Kind of another comment about this phase diagram, they gave this as X, and we think, well, what is X? Traditionally, X is, at least people drawing phase diagrams, we consider this an atomic fraction. And the way that you can verify that for yourself is by looking, for example, over here, right? Here we have Al3Ni, and it's at 25% or 0.25, and this is giving us a 3-to-1 ratio. So it is 75% aluminum, 1% nickel, or sorry, 75% aluminum, 25% nickel, and that's 25%. So this tells us that it is that X is referring to mole fraction or atomic fraction. And I want to show that here's another phase diagram. We're not going to look at this one in detail. This is titanium and copper, and all through here we have these line compounds that are forming, and two-phase regions. And the same thing we did with the previous phase diagram, we could take and do the same thing and map them out, and then we would know what phases are present. And this is something you should probably try practicing in order to know how to do it. And of course these are binary, but we know that most materials are not, at least most engineering materials are not simple binaries anymore. We're actually looking at compounds that are mixtures of multiple 3 to 4 to 5 different constituents. And this is one with 3. This is called a ternary phase diagram, and this diagram is SiO2, magnesium oxide, and then aluminum oxide. And if you look at this, right, we have a lot of these phases you've seen before: cristobalite, tridymite, molite, and then over here with Al2O3 you've got corundum, and then spinel. These are two common phases of Al2O3, and then MgO. So in this case, we move to a new way of representing the phase diagram using a ternary type structure. And I'm going to just briefly show you this so you can see that when we talk about these type of ternary structures, what we're actually doing is we're looking at a three-dimensional structure now. So whereas in our binary we had temperature on the y-axis and composition on the x, well, now these are all composition, 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 which means the temperature is now coming out of the board, which means that you actually are thinking about a three-dimensional structure where these are now surfaces in 3 dimensions. And you can take these and move from being in 2 dimensions to 3 and even to higher. So there's these big thick volumes, these 3-inch wide tomes of phase diagrams from the American Ceramic Society in which you have 3-dimensional and 4 and 5-dimensional phase representations of systems. So that was what I wanted to cover about phase diagrams, just giving you some examples and showing you a few examples of what you can do with them.